Welcome to the pre-class video assignment for section 111. This section is basically just a bunch of different applications that we can now solve using some of the methods we've learned. That's basically the approach here. What we're going to do here in this section, the first application, exponential growth or decay. I'm just going to cover that here, the first 2 pages. So you will cover that for you here in this section, and we will cover the other applications together in class, though we will look at some of the integrals that will come up here in this video. So the first application which we shall look through, exponential growth and decay. This is an application that you have probably worked with. They generally do come up in algebra classes. What's usually left out in an algebra class is basically where the solution comes from in an exponential growth or decay situation. But we can now rather easily derive the solution, the model for exponential growth and decay using differential equations. We now have the tools to do that with. So an exponential growth or decay, the model is the following: dA dt. So if A, capital A, is the amount of some quantity that is either growing or decaying exponentially, then this is the model that says that the rate of change, dA dt, is proportional to A. That is, the rate of change is proportional to how much material there is. So this is like saying population growth, if it's exponential, the more population there is, the faster the growth. This would be a statement of exponential growth. So basically, this is a differential equation, and it is actually quite easy to solve. It happens to be both separable and linear, so you can use either method. It's probably easier just to use separable equations here. Separating, we would get that 1 over A dA equals K dt, where K is a constant. So integrating here, we get ln of A. On the other side, integrate the constant K, we get KT, and then we get this, again, constant of integration generated, that we've combined the two constants from both sides into one constant on the right. We then can apply exponentials on both sides. So we have the absolute value of A equals e to the kt plus c1. Notice that exponential rules, we can write this as e to the kt times e to the c1. If c1 is an unknown constant, we can write e to the c1 as a single sort of aggregated constant. In this case, we're just calling it c. So e to the c1 can be written as just c, so we can now write that absolute value of A equals c e to the kt. But notice this is kind of strange in math here. Technically, c, if c is equal to e to the c1, c must be a positive quantity. E to the power of anything is positive. Think of the range of E. So that it would have to be positive. But notice what we can do here then. If I want to get rid of the absolute value bars here, then I can just get rid of the absolute value bars and allow the C to also be negative, and we can, again, take care of our equation this way. So we get that this amount of material growing or decaying exponentially is equal to c e to the kt. So this is the model that I am sure you are familiar with. This actually works for exponential growth and decay. If you have exponential growth, the k number is positive. If you have exponential decay, the k number is negative. You can see that here as well. The rate of change of A is, if it's a positive k, it's growth. If it's a negative k, it's the decay. So again, just some examples of this model, using this model. Once you have derived the model, you don't really need calculus anymore. These questions are really algebra questions, and I imagine they're the sorts of things you've seen before. So here are some examples. So let's say the population of bacteria in a culture grows at a rate proportional to the number of bacteria present at time t. That first line here is a statement that you should read as saying, hey, this population of bacteria is growing exponentially. So a population that grows at a rate proportional to the number of bacteria present is describing this model. And all we really need to understand from that is that we're being told that it is exponential. That means we can use this model. We are told after 3 hours, it is observed that there are 400 bacteria present. That means that this must be true. A of 3 is equal to 400, which is C e to the 3k, where time is in hours. We are also told after 10 hours, there are 2,000 bacteria present. That can be written mathematically this way. So A of 10 equals 2,000, or 2,000 equals C e to the 10k. We then have basically two equations in C and in K that we can solve. So if they are both equal to C, you can so if you set them both equal to C, they must set those two equal to each other. You can then solve this for K. So divide both sides by 400 and add or divide both sides by e to the negative 10k. So e to the negative 3k divided by e to the negative 10k is the same thing as multiplying by e to the 10k. So you get e to the 7k. And then take ln on both sides, and we get that k is ln 5 over 7. As a decimal, this is 0.22992. I rounded this to 5 decimal places. Again, working with this sort of thing, you want to keep lots of decimal places. Do not call this 0.23, otherwise it will be fairly inaccurate. So try to keep at least 5 decimal places, I would suggest. Again, this K number is can also be thought of as a relative growth rate, in that sense, relative as in percentage. This tells us that this population of bacteria is growing at about 23% per hour, because T was in hours. So this is our relative growth rate. So the K is always the relative growth rate, the percentage growth rate, but quoted as a decimal. So if we plug in that information, at least approximately, we get our model A of t equals C e to the 0.22992t. You can then find C by plugging in either point. By doing that, I get C to be 201. So basically what we get here, again, if C is 201, this is our model. And as you probably realize, when you put in 0, A of 0 is 201. So this C number is always the initial quantity. So in this case, apparently this population of bacteria started with 201 bacteria initially, at least approximately. We did round. Again, so I would imagine you have worked with that sort of thing before, but we will see some exercises like this, so practice on some of those here. So there is one on my open math to try. Okay, so the other classic example of exponential growth and decay is a decay model that is a radioactive decay. So our second question here, suppose initially there are 1,250 grams of some radioactive material. After 5 hours, 10% of the material has decayed away. So assuming exponential decay, basically find the model. What is the relative decay rate? Notice that we've already been given the initial quantity. So if we know what the relative decay rate, the K number is, then we have our model. So again, our model is this sort of thing. A of t, amount at time t, is A0, initial amount, times e to the kt. So we already know our initial amount, that was just given. So that is A0 is 1250, and we want to find K. So we can find K from this information. After 5 hours, 10% of the material remains. So when T equals 5, we have 10% of the material has decayed away. 90% of the material remains. So 90% of 1250 is 1125. So A of 5 must be equal to 1125. So it must be equal to 1250 e to the 5k. So we can set these equal to each other and solve. You might notice that maybe this was overkill a little bit. If you divide both sides by 1250, guess what? You get 0.9 equals e to the 5k. So that is our 90% equals e to the 5k. Take ln on both sides. We can come up with a k number. Thing you'll notice, of course, is that the k number is now negative because we have an exponential decay. We are decaying away, but this is still a relative decay rate. So this K number tells us that the radioactive material is decaying away at about 2.1072% per hour. I apologize with some of the writing on these kind of gets jacked around a little bit when you save it to PDF. Hopefully that is still legible. So we can actually do some other follow-up questions. What is the half-life then? And this is actually fairly common that in radioactive questions, the way a material, the speed at which a material decays away is quantified by half-life instead of the K number. So what is helpful mathematically is to be able to switch between the two. If you're given the K number, you can find the half-life, or if you're given the half-life, you want to be able to find the K number. So let's talk about that. So let's suppose capital T is the half-life of our radioactive material. Then at time T, if you plug in that time into our model, we should have half A0, half of what we started with left over at e to the kt. That is the half-life. So notice the amount of material that you started with doesn't matter. The half-life is the same. So that is this little statement here. Notice that in exponential decay, half-life is a constant. It doesn't depend on how much material there is. The half-life is a constant. So then we get this relationship: 1/2 equals e to the kt. So in our example here, we found K previously. So if I plug in the K value, I can take ln on both sides and then solve that for T. And I get this to be 32.894 hours. So the half-life of this particular radioactive material is 32.894 hours. That means that if you start with 1,000 grams of this material, after 32.894 hours, you will only have 500 grams left. And in fact, if you start with 2 grams of this material, after 32.894 hours, you will only have 1 gram left. This is our half-life. A kind of helpful little spot here to take a look is this guy here. If we solve that guy there before we plugged our K value in, you can actually come up with a formula relating T and K together. This is quite helpful. If you have the K number, you can compute the half-life by this little formula, and vice versa. The formula is basically the same either way around. That is, if you solve that formula for K, you get this sort of the same formula, that K is ln of 1/2 divided by T, and T is ln of 1/2 divided by K. That is a shortcut for making this connection between half-life and the K number. So you don't have to think it through every time. You can use a formula there. The last question here is pretty straightforward. How long does it take for our radioactive material to decay down to 100 grams? So that is, we started with 1250. If we end with 100, we can set up that equation and simply solve for T. So again, this is not too difficult to do. Divide by 1250 on both sides, take ln on both sides, solve for T. I got this to be about 120 hours. So roughly 120 hours. So again, we should be able to do some exercises like that. So a little example on my open math to try for you. Okay, so the only thing then is, well, we will be going through the rest of these examples, the rest of these applications together in class. There are a few different types here to talk about. One we will talk about here briefly. Well, not really going to talk about it, but we are going to do something called Newton's law of cooling. We run into some integrals here. So this particular little integral, it's not terribly difficult. If there's anything confusing about it, is all the letters flying around. So I'm going to have you try one of those here on my open math. All right, so other prerequisite or other preview integrals we're going to look at. We're going to look at mixtures of salt solutions. So again, we will go through this model and this application together, but we run into a certain type of differential equation when we do this. They're not difficult, but we're into things like this. If you look at this guy right here, you will find that this is actually both separable and linear. I have solved this particular one here by the linear method, but you can also solve this by the separable method. That would the first step here to do separable would be to combine these two terms into a single fraction on the right-hand side, and then you can separate. So that is a little exercise for you to preview on my open math. And then last but not least, we have another mixture problem, and a different mixture problem that kind of works out a little more difficult. We end up often, again, we will talk through the derivation of this dE, but for now, just I'm going to look at how to solve something like this. Turns out that this one is linear but not separable. So we're going to have you try and do this one by a linear method. Again, our first step would be to write it in its standard form. You can then see the p function here and use that p function to come up with your integrating factor and so on. So it will be something like this on my open math. And that's it then. That will be what you need to look over for this pre-class video assignment. Otherwise, we will call it quits here and we will finish this in class together. Thank you.